In this last part, we're going to discuss three things. The dot product as it relates to a concept called work. We're going to talk about a special scalar called the component, and also the special vector called the projection. In a typical word problem in physics, you talk about find the work in moving this red particle to the blue particle, and you talk about a constant force, and you're going to move that red particle to the blue particle some distance d. But let's call this vector a force vector, and let's call this distance a distance vector. And then we've got this all-important theta here. Alright, so the important thing here is we want to know how much of this force applies in the direction of d. So I'm making in yellow this here. We're interested in how much of the force applies in the direction d. So this yellow vector is ultimately what we're going to call the projection vector, the projection of F onto d. But for the illustrations here, we're going to talk about the magnitude first. So let's talk about this vector as the magnitude. It's a constant in this first illustration. And then this distance would be magnitude here. So we know work done by F along D. We know that work is equal to force times distance. But the force that we are really concerned with is the force, part of the force that's applied in the direction of D. Through some basic trigonometry, the force in the direction of D is going to equal the magnitude of F times the cosine of theta. And then we're going to multiply that by the distance it's traveling, which would be the magnitude of vector D. It is this formula that you might use in a typical introductory physics course. Now if I just rearrange this because it's all multiplication, associative and commutative properties, magnitude F, magnitude D, cosine theta, and by the theorem that we proved earlier, this is going to equal vector F dot vector D. And this illustrates then that work is equal to vector F dot vector D. So it's the work done by vector F as a particle moves along D. You're going to probably have the temptation to use this when finding the work, but you can use that for two-dimensional. But suppose these vectors go in three-dimensional space, you're going to need the dot product to find the work. Now we take a look at the component and the projection. Alright, let me pick a color here, pink. So suppose pink is this vector. Hopefully that shows up nicely. Suppose pink is this vector here. Specifically, that is the vector that if we drop perpendicular down 90 degrees here, then that pink is a vector, and that's called the projection of F onto D. The projection of F onto D. But before we discover what the formula for that is, we're going to talk about the pink vector's magnitude, which we will call the component of F along D, or often called the scalar projection of F along D. It's a scalar value. It's the magnitude of that pink vector. It's also along or onto D. It is notated comp F onto D. Notice the D is lower, so F is onto D. Again, I can't emphasize enough that this is only a scalar value. Now using trigonometry, we know that that is simply magnitude of F times the cosine of theta. So that is the desired result, but we're going to write it in a different form. Using the corollary of a theorem before, we're going to say magnitude of vector f, but then cosine of theta can be written as vector f dot vector d over magnitude of vector f times magnitude of vector d. You might see here that the magnitude of vector f cancels out, and we're left with simply vector f dot vector d over the magnitude of vector d. It can be written that way, and it is often written like this as well. Vector d over the magnitude of vector d dot vector f. Again, this is a scalar, and it gives us the distance from here to here of this vector, which is also called the projection vector, which is exactly what we're going to find now, the special way to express that projection vector. The projection of f along or onto d, or we can simply say vector projection of f along or onto d. Writing it this way, we can see that we have a vector versus me saying scalar projection. That helps to clarify exactly which one we're trying to find. Okay, so the projection vector is denoted proj f along d. Again, d is below because it's on to d. And let's see if we can't discover this. The idea here is that if we could find the unit vector, remember unit vector, which I'm drawing here in yellow, has a magnitude of 1. If I had this unit vector and then took the unit vector times this scalar, it would give me the desired projection vector. So this little unit vector then, I'm just going to write it as, I'll write it over here, as the unit vector in direction of d. So it has the same direction as d, but it's a unit vector, a magnitude of 1. So we would need to multiply that then by the scalar, which we have already defined as the component of f on to d, and then we have to multiply those. So we have here the component of f along d. We have already discovered that to be vector d over the magnitude of vector d times, dot vector f. And then we need to multiply that by the unit vector in the direction of d. And if you follow carefully, you realize that that's vector d over the magnitude of vector d. And then we just have to order this around a little bit. Vector d dot vector f, let me highlight that dot, times vector d all over the magnitude of vector d squared. And there is our second formula, which I will summarize below here. So the projection of f onto d, is equal to vector d dot vector f times vector d all over magnitude squared. So this operation here is just multiplication, because the d dot f dot product will be a scalar, and then we apply that scalar through multiplication to the vector d. Now your book won't use f and d per se. They will use these vectors b and a, and we'll talk about the projection of b onto a. Again, the two things, the component of b onto a, and then the projection vector of b onto a. And let's see if you can't write that formula now, pressing pause, and then make sure you have it correct. So here are the two formulas that you should commit to memory. One of the things or ways that people can memorize, it's onto a is in the bottom, so it's in the denominator, and same thing here.